Okay, so it's a great pleasure to have Simion Filip from University of Chicago, and he will speak about degeneration of Kähler forms on K3 surfaces and some dynamics. So please, Simion.
Yeah. Thank you so much for the introduction, and also thank you for the opportunity to speak here. I know that the topic of this seminar is more perhaps closer to symplectic topology. I'll try to mention some things that are symplectic in various ways. We'll see that kind of symplectic forms appear quite a bit in this talk, but a lot of the flavor of the talk is going to be more about kind of symmetries, and in fact, large groups of symmetries of K3 surfaces. So I'll define K3 surfaces and I'll explain why they're interesting from the point of view of dynamics. I also hope to say a few words about these pictures, so you can probably see these kind of fractal-like objects and what they have to do with the dynamics of automorphisms of K3 surfaces. So the automorphisms I'm talking about, they're certainly area preserving. So from that point of view, they are symplectic, but the kind of questions that I want to ultimately understand are less about kind of periodic points and more about kind of more geometric hyperbolic dynamics type questions. But let me begin by just kind of setting up a little bit of notation and reminding you the concepts that I want to talk about. So X in this talk is going to be a K3 surface. So what's a K3 surface? So I will think of it as an algebraic surface, meaning as something cut out by some polynomial equations in some ambient space. And it's equipped with a two form. So surface here means that the number of equations is 2 less than the ambient dimension, so you get a surface in that sense. And so the symplectic form is algebraic in the sense that it's given again by polynomial equations, by polynomial functions and polynomial expressions in local coordinates. So one thing that is maybe important to emphasize is that once you work with polynomial equations, you also have to specify what field you're looking at. And for the most part, I'll talk about the complex field, but I'll get to that in a moment. One condition that I do want to impose is that it is simply connected. So in dimension 2, you can also think of complex two-dimensional tori. And these are algebraic surfaces, and they certainly have a symplectic 2 form, which you might think of typically writing as DZ1 wedge DZ2 in the appropriate charts. But those are not algebraic charts. But if you were to write them, if you were to write your complex torus in some projective space cut out by polynomial equations, those equations would be quite complicated. But the 2 form would still be expressed by polynomial equations. However, if I impose this simple connectivity condition, I exclude the tori. So let me say this to exclude tori. And this is kind of an important point that we want to restrict to this simple connected class. So there is no first homology of these surfaces. The other remark that I was making earlier is that because I'm working with algebraic objects, I have to specify the field. So I'll always take the complex points. So a complex surface means in this talk, complex 2-dimensional, so real 4-dimensional. So we're talking about real 4 dimensions. However, I will at the end hopefully make a few remarks about what happens over other fields and why that might be interesting and not kind of completely unrelated to more symplectic questions. Okay, so this is the just the definition. Then a key object associated to any expressions in the Ron severity group. So what is it? Remember, if we have a surface, we have H2 with integer coefficients. So because I assumed my surface is simply connected, It also means that there's no H1 and no H3. So the only interesting group is H2. Incidentally, all K3 surfaces have the same topological type. So this has rank 22 over Z. And the Néron-Severi group is the combination of this first cohomology group with the part that supports interesting Kähler forms, or it doesn't have to be over R, just H11. So because it's an algebraic surface defined over the complex numbers, it has an additional Hodge decomposition of the cohomology, and it has H20, H11, and H02. So let me just remark that omega, the 2 form, really lives in H20, meaning that it has locally kind of a DZ1 and a DZ2, whereas H11 means things with DZ and DZ bars. And so you intersect it, and this is the definition of the Néron-Severi group. And it kind of combines the topology and the complex analytic structure. So the rank of the cohomology is 22. The Néron-Severi group, well, is at most, I'm gonna say, 20-dimensional, because the 2-0 part, there's also 0-2 part, so that takes away 2 dimensions. And rho is going to be the rank of this group, so it's a very important invariant of our surface. And rho equals 1, rho is at least 1 because it being an algebraic surface, it lives in some projective space, so it has the Fubini-Studi form from there, and that's a cohomology class that lives both in the integral part and the H11 part. Okay, so this is so far the notation and just the basic objects. Are there any questions about what the different things mean and what are they? All right, so if not, then I'm gonna mention now a few standing assumptions. They're mostly kind of to simplify the exposition, so that what I say is accurate, and also to kind of make the situation more interesting. So this is, if some of these words don't make sense or are maybe a little bit confusing at first, you can kind of ignore them, but I just want to make them at the start. So the first assumption is that this rank rho, I'm going to assume it's at least 3. So you'll see in a moment why this is irrelevant. The reason is the next assumption, which at first might seem like a very strong assumption, but in fact, I want to argue that it's not a very serious assumption. There's ways around it, but I'm going to look at the automorphism group of X. So the set of all complex analytic or algebraic automorphisms of X. And certainly this group acts on this Néron-Severi group. So one thing I should have specified is that cup product on Néron-Severi group, it has signature 1 rho minus 1. So there's one positive direction and rho minus 1 negative directions. So the automorphism group maps to this indefinite orthogonal group. And I'm going to assume that it's a lattice in this indefinite orthogonal group. So this assumption is, in fact, quite typical of, this situation rather, is very typical of K3 surfaces. And in fact, in higher dimensions, there's something called the cone conjecture for all Calabi-Yau manifolds. And it predicts something along these lines. In other words, that the automorphism group is fairly large. So in general, it's not necessarily a lattice even for a K3 surface, but still there is some kind of finite fundamental domain in some hyperbolic space. So the reason why I'm talking about hyperbolic space is because, of course, this signature 1 rho minus 1 leads to hyperbolic spaces. If you take the vectors of 1, you obtain exactly a hyperboloid. So this assumption is not, as I said, a very strict one, even for K3 surfaces, and things can be analyzed in general. I see. Any other assumptions? Yes. The other assumption that I want to make is that so I'm going to talk about elliptic fibrations, meaning that on my surface X, I'm going to fiber it in elliptic curves. So what this means is that my form manifold is going to be a torus bundle of a two-dimensional, a real two-dimensional base. And I want to assume that the fibers, so in everything that I say later on, that the fibers are just kind of the simplest degenerations, things like this, not anything more complicated. So this is just to kind of simplify the statement. Okay, so any questions so far about anything that I said? No. All right, so let me move on to an example just to illustrate where all of these conditions are satisfied. Maybe one thing I should have said is that this condition rho greater or equal to 3 is to make things interesting, because of course if rho is 2 or less, then this indefinite orthogonal group is well, not so interesting. SO11 is basically R. And so I'm interested in kind of large non-abelian groups. So rho, that's why rho is at least 3, so that rho minus 1 is at least 2. Okay, so here's a standing example for which everything that I say is already interesting. So here's an algebraic equation. So it's in 3 variables, x, y, and z. It has degree 2 in each variable. So each variable appears at most a power 2. I'm saying that it's in P1 cross P1 cross P1 to specify how to look at this equation in homogeneous coordinates. So strictly speaking, this equation is in a affine 3 space, and I need to compactify it, and I want to compactify it in this product of P1s. So so here's a picture of how this looks like. What happens is if you, for example, in this picture, I froze one of the coordinates. So let's say the x coordinate is picked to be some constant. So then I get some curve on the surface. This curve is going to be an elliptic curve. In other words, it's going to be a real two-dimensional torus. And in some sense, K3 surfaces are kind of higher dimensional, as you know, Calabi-Yau manifolds in general, having a holomorphic n form and n dimensions is kind of some form of generalizing the idea of an elliptic curve. The reason why, okay, so let me tell you a little bit more about the structure of this. So because we have 3 factors of P1, then our neuron-Severi group has rank at least 3. I should say that in general, to show that the rank is precisely 3 is actually a very difficult question, because I have to convince you there is no other algebraic cycle on this manifold. But let's assume that the rank is precisely 3 and not larger. And this is the intersection pairing. So each curve like this has self-intersection 0, because I can just move it off itself by taking a different parallel section. But any 2 of these curves, so if I freeze another coordinate, then I would get 2 intersection points. So of course, this picture is for the real points, but I'm thinking of the complex surface. So it's really complex two-dimensional, the picture that I have in mind. And now the automorphism group, the dynamics, comes from the following collection of involutions. So there's a formula, but let me explain where the formula comes from. So if you, again, think of y and z as constants and x as a variable, then you get a quadratic equation in x. So you have x squared times some constant plus another term times x plus some remaining constant. And a quadratic equation has 2 solutions, and you have an automorphism that exchanges the 2 solutions. And this is the formula for that automorphism. And so this 5yz is the term in front of x, which is the sum of the roots, if you put the minus. And then I normalize by the term in front of x squared, and I subtract one of the roots. General theory of quadratic equations tells me that this will be another solution of this quadratic. So if I plug in this expression instead of x, then things will cancel out and yield another solution. So a different way to describe the same automorphism is that if you kind of project this onto the, I guess here's the YZ direction, then this map is 2 to 1. So except it has a branch locus, but you can exchange the two sheets, and that is what this map is doing. And you can do this. So of course, if you do sigma x twice, you get back the identity map, but you also have sigma y and sigma z, and composing them in different ways, you get more and more complicated expressions. Okay, are there any questions about this example? No. All right. So let me then define tell you a little bit about what the ample cone is. So as I said, in this example that I gave earlier, we have the Naran-Severi group, which, as I said, has signature, in this case, 1, 2. And here I have the classes, cohomology classes alpha. Let's say the cone is actually where they're greater than 0 or greater than or equal to 0. And of course, there's the bottom cone. There's a cone over here on the other side, but I want to ignore this one. So there's one distinguished component. And here I have the hyperbolic space, which is the classes that square to 1. And if you look at this picture from the top, you will get, so again, this is a picture of the hyperbolic space. And the three cohomology classes corresponding to the, the three cohomology classes corresponding to the three coordinates that I said were those elliptic curves, they live really on the boundary of this hyperbolic space because they have self-intersection 0. So they give you 3 rays in this picture. And you have the 3 involutions that I drew, that I described, I described earlier. So if I apply, for example, sigma x, then what you can observe is that if you compute its formula for it in coordinates, it will preserve a hyperbolic geodesic, and it will act as a reflection in, it will take this ideal triangle in hyperbolic space to this new ideal triangle. And so in particular, it will give me another elliptic curve. And you can keep doing this, and you get a tessellation of the hyperbolic plane into these kinds of ideal triangles. So one thing that will be important is the boundary of this ample cone. So the reason why this is called the ample cone is because you want Kähler metrics that can also be represented as linear combinations of first Chern classes of line bundles. So this is why we restrict to this region, not all Kähler metrics, but just the ones that can be represented by Chern classes of line bundles. And then we get this large automorphism group that essentially acts with a finite fundamental domain on this hyperbolic space with these involutions. And as I said, I'll be interested in the boundary. So in the classes that have self-intersection 0, which in this case, when you projectivize, I drew them as this circle. And TBE means to be explained. I'll explain that, in fact, we need a variation on this object, which I denoted by this. It's a construction that involves certain blow-ups, but I'll explain that once I've introduced more notation. But what is important to remember is that there's the boundary, and then we have to sometimes do some points.
I'm sorry, my sound was distorted. Could you repeat what was important to remember?
So what was important to remember was that there's this ample cone, the interior where you have self-intersection strictly positive, and its boundary where you have self-intersection 0. And I'm going to think of it after I projectivize as this circle in higher dimensions is going to be a sphere with the boundary of hyperbolic space. And on this boundary, I have rational directions that correspond to these elliptic curves. And there's also all the other points, which are the irrational points. And this notation for this slightly modified space, I'll explain a little bit later in the talk, a way to modify this boundary from a sphere to something a little bit more complicated. All right, any other questions? No, all right. So let me then move on to, as I said, why I think K3 surfaces are interesting for many purposes. So we're gonna, as I said, work with 1 over the complex numbers. If you have some Kähler form on X, then a theorem of Yau tells us that there exists a unique other Kähler form omega, which induces a Ricci-flat metric. So if you have a Kähler form, you can think of it as a symplectic form, a 1-1 form, alternating, but you also have a metric, and this metric is a Riemannian metric, is Ricci-flat. Well, there exists a unique such Kähler form, which in addition is in the same cohomology class. So this is a theorem in PDEs. It's saying that a certain PDE has a solution, PDE given by this Ricci-flat condition. And in fact, the condition can be expressed in terms of the symplectic form, holomorphic symplectic form omega. And the condition is that omega wedge omega is equal to omega wedge omega bar. But so the Kähler form squared is equal to the volume form induced by the holomorphic symplectic form. So both sides locally look like dz1 wedge dz1 bar wedge dz2 wedge dz2 bar. So, and of course, well, okay, you have a function rho, which is not a good name, f. So locally, you have some volume form, and the Kähler form, little omega, has to satisfy that it's equal, that its square induces this volume form that's prescribed. And in general, that's not kind of an easy equation to solve, so it leads to something that's called a NonJupiter equation. More importantly, K3 surfaces are examples of hyperkähler manifolds. So what that means is that not only do you have one Kähler form omega, but in fact, if you use the real part of capital omega, the imaginary part of capital omega, then they themselves are Kähler forms for a triple of complex structures I, J, and K, which satisfy the usual quaternionic relations. So not only is, and in fact, all of the corresponding Kähler metrics, if you use this triple, they will also be Ricci-flat. So in some sense, you have one single Riemannian metric, this Ricci-flat metric, corresponding to this cohomology class, but then you can rotate and obtain a whole sphere's worth of symplectic forms coming from that one Ricci-flat metric. So all of this is kind of the one point I want to make, that the metric itself is intrinsic, but well, once you fix this one cohomology class, but these 3 different symplectic forms can induce the same metric for different complex structures. All right. So as I said, I was going to be interested in the metrics and what's happening to the metrics. So how do they degenerate? The typical situation that people study is the following. You have a base, your surface X, and you have a complex one-dimensional base B, which will have to be isomorphic to the complex line. And so you have a picture that looks like this geometrically. You have some singular fibers. So this is the picture over the real numbers on the right. And so this is what's called an elliptic fibration. So if you were to draw the geometric picture, you would something like this. So over some points you have honest tori, and over other points you have singular tori. and the base is a sphere. And what is typically looked at is the following. You take, so remember, Yau's theorem says that in every cohomology class, there's a unique Ricci-flat Kähler form, preferred Kähler form. And what we're going to look at is, if I prescribe the cohomology class, then there's a unique metric. And the cohomology class is required to be the following. So XB is the cohomology class, the dual to the fiber. And T is a parameter. Parameter here goes to 0. So what we're doing geometrically is this. We are giving less and less volume to the tori, the fibers, because the fibers have self-intersection 0. So if you were to integrate this cohomology class over the fiber, you would get just T. Omega 0 is some fixed reference Kähler class. So what this basically means in the cone picture that I was drawing earlier is that here is your homology class of the fiber, and you are just approaching in a straight line that rational class. Let me just remind you that this is not normalized to volume 1. So this is the hyperbolic plane, and we're really here going in this direction. We start, let's say, omega 0 has self-intersection 1, but as we degenerate, we are decreasing the volume. So, but yeah, because we're decreasing the volumes of the fibers. And so this has been studied a lot, I think, in the context of a mirror symmetry, and the properties of this have been looked at by Gross and Wilson and Tosatti and many other people. The goal of what people want to show in general is some statement that as a metric, as a Riemannian metric induced by omega t, you have a convergence to a sphere with some singular points, and these tori degenerate and get smaller and smaller, and the metric that you obtain on the sphere in the limit is some metric with special properties. Importantly, you converge not only kind of in some weak sense for the metrics, but in this Gromov-Hausdorff sense. And the metric, there's one way to define the metric, which is you have a volume form on the total space. You can push it down and you get a volume form on the P1. And if you have a volume form on P1, that's a 1-1 form, and you can view that itself as a Kähler form. And that is the definition of the limit metric, but it's a rather challenging thing to prove that this is true. Now, what I want to concentrate in this talk is to ask what happens for all the other points on the boundary. So what I mean is, if you remember the picture from before, we had something, oops, so not good. We had these elliptic curves, and so we kind of went in this direction. This was the degeneration we're looking at. This was a rational point. And what I want to ask is, how about, if I just pick a random point on the boundary, what happens if I start changing my Kähler class in that direction? So this is the question. Of course, the rational points are only countably many, and the irrational ones are uncountably many. So this is what we would like to understand. So let me say now what the theorem is. So the theorem about C is for currents, and the theorem is that there exists a unique map eta from this boundary. So if you remember, I was talking about this boundary of the ample cone. So roughly speaking, as a first approximation, you can think of this null cone, but eventually we'll have to modify it to something a little bit more complicated, but ignore this for now. And it's a map to 1-1 currents. So Z, this is a curly Z, 1-1 currents which are positive. So just as a reminder, currents is the same thing as differential forms with measure strictly speaking, distributional coefficients, distributions in the sense of generalized functions, but once you have this positivity, you can actually improve the regularity and say it's not some arbitrary distribution, but it's just measures with measure coefficients. Measures in the sense of Rodin measures, they could be also negative. So once you have this positivity property, so it's some abstract space, but what is important is that this map is unique, and it has a lot of, it can be characterized in a number of ways, but it has a bunch of very nice properties. First of all, it is equivariant for the action of the automorphism group. So the automorphisms act on this null cone, and they also act on positive currents, and this map is equivariant. It is continuous when you put a weak topology on the currents. In fact, you can put a slightly better topology on the currents, but to make that statement, I need the next property, which is that these currents have continuous potentials, which means that locally on X, a current, one of these currents that I'm interested in, is ddc of some function phi, where phi is some continuous function. Let me see. And furthermore, these currents are essentially the unique positive representatives in those cohomology classes. So there's no other positive representative in that cohomology class. This was announced by Verbitsky and Sibony, and also proved in various other settings also by other people. So what this uniqueness means is something like this. So let me go back and compare it a little bit with the picture of the elliptic fibration. So again, I'm drawing half the picture and half the dimension. So these currents, in the case of an elliptic fibration, they're just basically you take, it's kind of an odd thing to do, but you pull back the push forward d-vol. So you can think of this as a transverse measure. Sorry. You can think of these currents in the case of a rational direction as transverse to, as a measure that's transverse to this foliation by the tori. So I can integrate this current over, say, any patch over the base, and it's kind of a geometric intersection number with this foliation. But here it's a periodic foliation, and of course, in this cohomology class, I can take any 1-1 form on the base, pull it back to the total space, and I'm going to get another cohomology class, another positive representative of the same cohomology class. Here, for the irrational directions, there isn't really a picture, but you should think of it as something like an irrational foliation on your K3. So this is X. And this is kind of a unique ergodicity statement. The uniqueness of these positive representatives is saying that there's a unique positive measure that's kind of transverse to this foliation. So,
sorry, I missed you here. How did you get foliation, this rational foliation?
Right. So this I didn't put on the slide, but in fact, we can also show that these currents, they have a property that's called weak laminarity in complex dynamics. So what that means is that they can be written as a sum. So the sum of something like this, it's a rather weak property, but it comes from hyperbolic dynamics. So alpha is some countable set. Well, not alpha, but I is some countable set. And each ti is the integral over, essentially you have a chart where you have some disks and a transverse measure mu. And you take an integral over d mu of these disks, d mu z, for a transverse foliation. So the thing that is very unfortunate is that there's very weak information about this foliation. So it's only something that, because of this countability and, for example, there's nothing known about the support of this foliation. So maybe foliation wasn't the right word. I think elimination is more correct. So I think many people conjecture that, expect that this is really a full support. In other words, at every point on the boundary, every point on X, in the neighborhood of it, you have some piece of this foliation. But so far, it seems like it's a very hard question. So it's not known that this elimination is actually supported everywhere. But you do have this property of writing it as a countable sum of these little flow boxes. So this is kind of the part that I think is kind of the most interesting to understand, which is to understand the actual geometry of these currents. We know that they have a representation that looks like elimination, but we would like to get more than just that. But so far, it's not known. Okay, are there any other questions? All right. So there's also a theorem that is kind of using completely different words, but it has almost the exact same proof. And this is a theorem, and kind of it's about number theory. Kind of has applications to number theory, but I hope to get to it at the end. And that is that there exists something called the canonical height. So I will say maybe towards the end of the talk, if I have time, what is a height. But the point is that you can, once you have this current over the complex numbers, you can try to do similar arguments at every p-adic place. And if you work over the rational numbers, then you can construct these height functions. So I will not describe this here, but I'll just say that basically it has the same kind of properties. So let me just say maybe informally, a height, what it does is it measures the complexity of a point with rational coordinates. And what you can do is now you can take some equations, you can take a point, a solution, and as I said, this height becomes a function on this cone. It's a homogeneous function, so P is a solution to my equations over the rational numbers, let's say. And I have a homogeneous function on this cone, homogeneous meaning that if I scale the array, then I scale the function. And what I plotted in this picture is the set. So I flattened the cone, first of all. So this cone really I brought it down to BR2. And in blue are the values, the cohomology classes for which this point has height 1. And if you scale it, you can compute all the other values. And you can see that this is a pretty kind of ragged curve. And this is how I think the currents in general will look like as well. They're going to be, their potentials are going to be only Holder functions and have all sorts of other not very easy to understand properties. However, there's also an expectation that they have some geometric structure, but that is kind of not yet understood. Okay, so let me say a few words about one of the main ingredients and the proof of this. And even though we're interested in the irrational points, we still want to understand the rational points very well. And what this has to do with is again, going back to the elliptic fibrations. So if I have my surface, if I have my surface X, that I fiber again in tori, and so I'm making these standing assumptions that the fibers are only nodal curves, so only the simplest type of singularities. Then what is going to happen is that my automorphism group that commutes with this map pi is going to be essentially z to the rho minus 2. So remember, rho was the rank of my Neron-Savary group. So I apologize for a moment. For some reason, my tablet is lagging. Can I disconnect and reconnect my just view? Is that okay? It will take one moment, I think. Let's see. All right. All right. Okay, now it's moving. Okay, my apologies about this. So the setup again is this: we have our surface, and it's fibered in tori, and I want to ask about automorphisms that preserve this fibration. In other words, that they act as translations on each torus, but together they give some interesting automorphism of the surface. And if you go back to this hyperbolic plane picture that I was drawing, what happens is if you have a cusp, then you can act as a parabolic automorphism that preserves this one rational direction. And so as a map of hyperbolic space, you preserve one point on the boundary and you kind of rotate in that direction. So this is what's happening geometrically. So remember here, rho was 3, so rho minus 1, the rho minus 2, I mean, was just 1. So we have only one such parabolic, such automorphism that commutes with the projection to the base. However, if rho is 4 or more, then you, for example, when rho is 4, you work in hyperbolic 3 space, and then your group of automorphisms that preserves the point at infinity will be in this hyperbolic space picture will be of rank 2. So you'll have 2 commuting automorphisms that preserve this boundary point. And so the theorem is the following. So one of the ingredients in the proof is the following, that if you have such an automorphism T that belongs to this abelian group, and omega is any Kähler form, then you can define the following limit. You apply the automorphism n times to your Kähler form and divide by n squared. So you would see that in cohomology, this is the correct normalization. So this new form still has self-intersection volume, gives volume 1 to the no, sorry, it doesn't give volume 1 to the fibers, but rather it's of norm 1 in the vector space. And then this limit, first of all, it exists as a current, and unlike the currents on the previous slides, it has good regularity, so it's essentially smooth everywhere except at some of the singular points of the elliptic fibration. What is more important is that it's independent of the starting Kähler form omega. So in some sense, it's really associated to the automorphism T. So if you think of your surface as, you have your twist automorphism, if you twist many, many times, eventually you start converging to something that looks like, that is independent of what you started with and only depends on your automorphism T. One thing that I should have emphasized is that this group Z to the of automorphisms, it has a different interpretation. Well, it has a kind of a more canonical definition, which is that if you are in a vector space of rank 1 rho minus 1, of signature 1 rho minus 1, if you take the orthogonal complement of a null ray, so you have the following kind of filtration of your vector space. In this total space, so you have your null ray, its orthogonal complement will contain the null ray, and the quotient space will have a positive definite or strictly definite metric if you take this quotient. So this is true in any vector space of the signature, that if you take an alloy and its orthogonal complement, the signature, the intersection pairing here is degenerate. Here it has one degenerate direction, which you quotient out. And when you quotient out, you get a vector space of dimension rho minus 2. And there's a positive definite metric. Yeah, what was the question? No. And so what the remark is that this map Q pi of t actually, you can view it as a pairing. So in fact, it gives you kind of a quadratic form Q from this 0 minus 2 into currents, into positive currents, that is compatible with this cohomological object, which is just given by integrating these currents. But essentially, if you take any automorphism and you iterate it and at times a normalized by n squared, you start converging to a positive current that only depends on the automorphism and not on the starting Kähler form. And this, as defined here, certainly has quadratic scaling. So if I replace t by t to the power k, then I'll get a k squared in front of this limit. But I can actually, you can actually show that this becomes a bilinear form if you kind of polarize it. And the way to prove this result, so it takes a bit of time, but one thing that before I say about the proof is that when rho is at least 4, you see that you have a kind of 2 limits on the boundary. So let me try to draw the picture when rho is 4. So you have the point at infinity, you have a hyperbolic 3 space, and the automorphisms of hyperbolic 3 space that preserve the point at infinity, they're generated by, they have 2 generators, so essentially a Z2. And you see that if you move around, this is plane parallel to the plane at infinity. This plane is called a horosphere, and if you move on this horosphere, there are different ways to go to infinity. Once rho is 4 or more, you can go kind of to infinity by following this direction or by following this direction. So you can iterate different twists to go to infinity. And in fact, they will give, I mean, you could ask, is it possible that they give the same current and the limit independently of how you go? And in fact, the answer is no, they're all different in an appropriate sense. So in particular, when rho is at least 4, they cannot agree with this Kähler form that comes, or this current that comes from the SYZ picture of mirror symmetry. So this elliptic fibration that was drawn here, it has a bunch of different naturally associated currents that are kind of transverse to this fibration. So you have this non-uniqueness that even if you kind of constrain things dynamically, there's still kind of this non-uniqueness. Okay, so maybe before I say a few words about the proof, let me stop and ask if there are questions about what this theorem is saying.
I have a probably very stupid question. So can one think, so before you had this lamination for irrational kind of classes, yeah? Mm-hmm. So can one say that elliptic fibration is analog of this lamination for rational class?
Yes.
So, so that's the picture. So basically the theorem about laminations was geometrization in the sense of irrational class for which you do not have a fibration.
Mm-hmm. Yes.
Okay, very good.
Yeah, that's right. The only remark though is that kind of logically, in order to prove that those laminations and those currents exist, we first have to prove this statement about these twists.
Sure.
So we first kind of have to analyze what happens when you kind of apply these twists many times, and you have to kind of deal with these other possible currents that exist on the surface. Okay, so let me just say maybe one intermediate step in the proof, which is, I think, kind of interesting, and is the following. Suppose that you have a smooth closed 1-1 form, omega on X, which integrates to 0 on every fiber. So this is a cohomological condition because it's just a closed form. So it's just a condition about its cohomology class. Then the assertion is that there exists a continuous phi such that, so I can modify omega by DDC of something continuous, such that on each fiber, it's actually identically 0. So let me say maybe one thing. For each smooth fiber, this is obvious because on each smooth fiber, so if suppose that I just freeze B, then I have a 1-1 form on a complex one-dimensional torus, which integrates to 0. Then certainly I can solve this equation to make it 0 everywhere. So I can cohomologically, so it's DDC of a function. If it integrates to 0 on an elliptic curve, then it's DDC of a function. And for all the smooth fibers, you can extend these estimates, and this phi will be smooth as you vary on the smooth locus. The hard part is to show that you can actually extend, you can make a choice. So this phi is not unique. It's well defined up to something pulled back from the base. So if I pull back from something from the base, DDC of it restricted to any fiber will be 0. So this phi is not unique, but the assertion is that there exists a choice of this phi, which gives you a continuous function on the entire manifold. So you can extend it at the singular points. So this is kind of a technical tool, and it's, as I said, on the smooth fibers, this is straightforward. On the non-smooth fibers, it's not so straightforward. And in fact, we're not exactly sure if this particular statement is true if you don't assume nodal singularities. So if your singular fibers look something more interesting, like a chain of P1s, or on K3 surfaces, you have not many possibilities for the singular fibers, but in fact, everything that I say here actually is true for any elliptically fibered surface, not just a K3 surface. So it doesn't have to be a K3. Okay. So let me just say a few words about the ingredients that go into the proof of the main theorem. So what we have to do is we have to take a look in the hyperbolic plane, and actually, let me try something else. So remember, we had this picture from the beginning. So what I want to do is I want to take a hyperbolic geodesic, let's say starts at the origin, and I want to go to the boundary. And what I have to do is I have to follow it as it crosses different fundamental domains. And basically, two possibilities are available in hyperbolic space. Either this geodesic will be recurrent, meaning that infinitely often it will come back to some fixed compact set in this fundamental domain. So I can take my fundamental domain here. So, and I can take some compact set, and I can take its orbit under the automorphism group. And this purple, there are two possibilities. Either this purple geodesic will come back infinitely often into one of these green regions in this fundamental domain, or it will not. So if it does not, then it has to go to a rational boundary point. So of course, here I have countably many boundary points. And if I just follow the geodesic for a finite amount of time, I don't know exactly which will it be rational or irrational. But if I follow it, but I do have this dichotomy. Either it's going to be recurrent. Sorry, what I wrote here is, of course, nonsense. I don't know if anybody was confused. I said it's either recurrent or recurrent. What I meant is divergent. For a rational point, it's divergent, because if I think of this triangle as kind of some moduli space, then really this is kind of a geodesic that goes to a point is divergent in moduli space. It goes out into the cusp. Okay, so we basically have to follow kind of code a geodesic like this, and then as we cross different fundamental domains, we have to glue together some estimates that we can prove for automorphisms. And what's important is the reason why we needed that statement about the elliptic fibrations is that we do have to kind of have a quantitative estimate on what happens when this geodesic spends a very long time in the cusp. So if you think of your moduli spaces, some finite volume hyperbolic surface, then the geodesic can spend a lot of time in the cusp, and then it might come back. And we have to understand what happens when this geodesic goes out into the cusp. And yeah, so we have to be very careful with these visits to the cusp. And that's why we need these estimates, and in fact, quite rather precise quantitative estimates for how the automorphisms act on these metrics. Maybe one remark is that in the Gromov-Hausdorff sense, the points, if you approach an irrational point, then you're actually converging to a point, because this recurrence in moduli space means that your metric is actually Gromov-Hausdorff isometric to something in a fixed compact set. So, and there's a rescaling that's involved. So remember, there's kind of the picture from above, which I was drawing in hyperbolic space. But really, what we are doing is we are diverging to infinity. The picture in hyperbolic space is this purple curve, but we have to always normalize so that we actually converge to a cohomology class. And so this point, the points along the purple geodesic, if it's a recurrent geodesic, it keeps coming back to some fixed isometry class of metrics. But when we rescale it by things that are larger and larger, so it converges actually to a point. So this is kind of a difference with the situation when you diverge into a cusp. Yeah, so I still didn't tell you what is this modified, blown up boundary of the ample cone. So one way to say it is that you have to blow up all the rational rays. So in dimension 1, this doesn't really amount to much, because if you blow up a point on a curve, you don't really introduce anything. But already once you consider dimension 2, so the boundary of hyperbolic 3 space, this is H3, here we have H2. If you blow up this point, what you do is you're essentially replacing this point by a little RP1, and then you have to do this uncountably many times at all the rational points. So this is, and then these things keep shrinking, and so this is kind of an odd space. It's not a manifold, but it does map to this ordinary boundary of this ample cone. There's a different way to define it. What you can do is, if you have your hyperbolic space, around each rational point, you can place a horosphere. So I'm drawing the picture, let's say in 3 space. So you can place a horosphere, and you have to place countably many such horospheres at each rational point. Of course, they're shrinking, so they're all disjoint. And if you remove these horospheres from hyperbolic space, then this becomes a cat0 space. So it's no longer negatively curved, but it's going to be cat0. Cat, as you know, stands for Kartan, Alexandrov, and Toponogov. I think in this seminar, there are a lot of French-speaking mathematicians, so you can also add Adamar, and so you can get the French version of cat0 spaces. But the point is that if you compactify it as a point in geodesic in this space with Hori sphere is removed, converge to infinity. In hyperbolic space, you could have just gone directly into this point, but here there are different ways to go around the sphere. So this is why you have to kind of glue in these bigger spaces. Okay, so I had a few slides just to kind of make a connection with, to explain what are heights and how does some of what I argued relate to that. But since I think I'm officially at the end of the talk, I'll just stop here. And if there are questions about this, I'm happy to explain it. It can take only a few minutes, but I don't want to go over time. So I'll just stop here. Thank you.
Okay, so thank you very much. So let's thank the speaker. So, well, I mean, we have quite a lot of time for questions and discussion. So please, I mean, go ahead. First of all, finish what you wanted to say, and then we will ask questions. Actually.
Okay. So what I was going to say is just a brief introduction to what are heights. This is a concept from number theory, and it's just a measure of the complexity of an integer or of any rational or algebraic number. So if it's an integer that's not zero, I just take the logarithm of the absolute value. And so maybe let me make a remark. Here I'm using what's called the logarithmic height, which is this little h. Sometimes you can see the big H, which doesn't have a log. So big H, if you've seen it before, it's the exponential of the little h. Now, if you're not an integer, but a rational number, then you define the height or the complexity. If you write your natural number as p over q in reduced terms, you take the maximum of p and q, and again you take the log. So if you have an integer, then q is 1, and more importantly, log of the height of p and the height of 1 over p is the same. So you kind of don't distinguish whether your number has become more complicated by kind of going up in size integrally, or kind of the denominator has gotten large. More importantly, and this is kind of a crucial point for what I want to say, is that if you represent your number a as a point in the projective line, so with coordinates p and q can be rational, but of course you can rescale them to be integers. Then a different way to define the height is to say that it's a sum over heights or complexities, contributions over all primes, including the kind of what's called the prime at infinity, so the real numbers. And this local height is given by this p-adic norm. If you don't know what the p-adic norm is, it's not important, but the point is that it's a norm on that if you complete Q with this norm, you get the p-adic numbers. And what is important, and this is kind of a crucial point, is that if you rescale A, then all of these expressions will change, but their sum will stay the same because essentially of the product formula. So there's an important point, which is that summation, or the product, since I'm saying it's a product formula, I should write it as a product. The product over all, for any irrational number, if you take these p-adic norms, including the one at infinity, then the product is always 1 for any a and q that's not 0. And so this is how these norms are set up in such a way that, sorry, the V is in the wrong place. So these norms are set up in such a way that their product for a rational number is always 1. And so you're really kind of measuring the variation here. If you rescale P and Q, then the quantity by which you rescale will cancel out over the sum. And so what does this have to do with currents? Well, in fact, it turns out that what you're really doing is, if you think of the genius coordinates as a point, the topological line bundle over of -1 over P1. So this is the total space of a line bundle over P1. If I don't think of P and Q as up to scaling, but actually as actual numbers, then this gives me a point in the total space. And in fact, I can put essentially any system, any metric on this line bundle will give me a height. And as long as they're compatible in some appropriate sense, then they will give me a notion of height. So these heights are not unique. This is one definition, but you can kind of axiomatize it, and any function that agrees with this one up to some bounded error is also a height function. And ultimately, it turns out that so, for example, if you take this the prime at infinity and you look at this function on the total space on C2, log max of Z1, Z2. So if you take its Laplacian, DVC, then you're going to get a closed positive current. So do you know what? So this is a question for you. That was going to end with a question, just kind of to jog your memory. What is the Laplacian of this expression? So maybe if it's more familiar, it's easier to consider log of max absolute value of Z1 on the complex plane. So this is a function on the complex plane, and if you take its Laplacian, you're going to get a measure. So what measure do you get? Which you can think of as a Kähler metric, a very degenerate Kähler metric, or a Kähler current on the complex plane. So before you ask me questions, I can ask you. No, I'm kidding. So I guess let me just say that what you're going to get is so the graph of this function, if you look at it radially, right, it's 1, and then sorry, it's 0 rather, and then it grows, and it's in fact this function is harmonic. Log z is harmonic. And so what you're going to get is you're going to get the uniform measure on the unit circle, because this function is harmonic inside the unit disk and harmonic outside the unit disk. This is the disk z and circle z equals 1, and it's 0 over here, and it's log z outside. And so when you take its Laplacian, it will give you a uniform measure on this circle. Of course, when you go to higher dimensions, you kind of get a foliated version of this picture. And the point I wanted to make was that essentially the way the proofs go for the existence of those currents over the complex numbers, they essentially can be applied almost word for word to get this kind of height function, which has kind of some interesting applications to orbits of rational points. So you can use these functions to study the growth of complexity of rational points on under the automorphism group. And if you study this complexity growth, you get a picture like the one I was showing earlier. So depending on which direction and the irrational points you go, this graph essentially measures the exponential growth rate of the complexity of your points. Like if you were to write them. So if you run these things on a computer, if you start with a simple number and you apply successively these transformations that I wrote down, so sigma x, sigma y, and sigma z, you can imagine that the complexity of these numbers grows exponentially fast. So if you apply n automorphisms, you would expect to have some coefficient times n digits for your numbers, and that's exactly what happens. So the blue curves tell you roughly what that coefficient is. So how exponentially fast the numbers are growing in size. So that's the little thing I wanted to add about heights, and I'll stop here for good for the talk.
Okay, thank you very much. So more questions, please.
Maybe I have a question. Simion, so have you thought of these currents from perspective of Lagrangian submanifolds after doing some sort of hyperkähler rotation?
So yeah, so in short, I think the answer is no. I guess the problem in some sense, I guess the reason why I haven't thought about this is, so in order to do hyperkähler rotation, you have to have an honest Kähler metric in order to do this. And so you have to choose a base point in your hyperbolic space. Whereas these currents, they kind of live at infinity on the boundary.
Mm-hmm.
So I'm not sure. So I don't know if there's some way to talk about hyperkähler rotation with respect to a boundary class, but yeah. So certainly these foliations, the leaves themselves are holomorphic, but the way they vary is certainly not holomorphic. So for this lamination, in fact, just because it's a lamination, that is one reason why it cannot be holomorphic in any way. So this is a kind of a picture that occurs a lot in hyperbolic dynamics, where you have some family of unstable manifolds, and the map, if you take two transversals, this map is a really kind of low quality map. So it's usually not really, it's only measurable if you try to define it everywhere. You could restrict it to some subsets on which it's going to be holder, but you can't get something of kind of better quality than that.
Thank you.
And I wonder, so if instead of complex structure, one will take an almost complex structure, as we do in symplectic topology. So do these laminations survive in any sense? Compatible with the original Kähler form, for instance.
So one question would be whether if you take an almost complex structure, whether you have a large automorphism group in that case. So
can you, so let's do the following thing. So start with one of your laminations, and I will just deform complex structure into almost complex structure. So can you deform your lamination to honest lamination, which is not complex, but almost complex? At least something from it kind of.
So I can't think. I don't think I would have to think for a second if such a thing is possible. But there's a simpler example. There's a simpler situation when some of these, I should have said that some of these results were known, which is, suppose that you have a single automorphism, a holomorphic automorphism. Then if you can apply this, and you'll obtain the same currents and the same objects. So let me say, so you have a holomorphic automorphism from X to X. And then there exists one of these currents, let's say eta plus, such that if you pull it back, then you get, it's scaled exactly by e to the lambda. So this is like a pseudo-Nosov structure. And strictly speaking, there's a plus minus, and then you have plus minus like this. So you have these currents. And my question is it possible to deform such that F still preserves the almost complex structure. Because this is kind of a very non-local condition, because you kind of have to control the space and the target, the source and the target.
Yes, that's of course kind of, yeah.
It seems quite difficult. That,
yeah, a bit unlikely, right?
But it's true that, yeah, somehow when you just consider one side, you have a little bit more flexibility. But yeah, I'm not sure.
You see. So,
can I ask maybe, I mean, maybe this is a bit of a naive question, but at the beginning you were explaining there are these rational directions that are of interest to the mirror symmetry picture, and then you were looking at these other directions. So what happens if you take what happens in one of these other directions and then you take the limit to one of the special rational directions? Does your picture, yeah, converge in some sense, or can you say anything about those special directions from the ones you consider?
Yeah, so let me make kind of two remarks about this. One is that unfortunately, it seems, I think it's very hard to, so even though these things vary continuously, it's kind of very hard to say anything interesting by passing to these kinds of limits. So to give you an example, what I think is reasonable to prove is that these currents have generically, so for Lebesgue almost every point on the boundary, they have full support. But I do not know how to show the same statement for one of these. And even though these are dense, so these, so to draw the picture, these these directions that are preserved by hyperbolic automorphism, they're dense on the boundary. I can obtain no new information, even though I can obtain lots of desired statements about the generic point on the boundary. I don't know how to propagate that information to these other points, at least the information that's interesting, that I'd like to know, that I think is true, but don't know how to show. On the other hand, if you look at, so at the rational points, one thing that I was saying was that if you take a rational point, draw it in blue, then there's kind of two currents here that you have in the limit. One is the one that comes from mirror symmetry, which is that push forward the volume, like that Gromov-Hausdorff limit. And then there's the other one that comes from twisting. So there's a there's an automorphism that preserves this point and that acts, kind of like as a translation along these Hor cycles. And then it converges. So there's this Hor sphere. And I expect in general they're different. If I take one of these currents that I constructed and I kind of limit it over here to this blue point, the limit will be, in the weak sense, in a rather weak sense, will be this kind of dynamical current. So let me call this one dynamical, and the other one mirror symmetry. Then the limit here on the boundary will be the dynamical one.
I see. Thanks.
Can you explain why, once again, so why you did these blow-ups on the boundary? So what was the purpose?
Yeah, so let me try to explain that. So let's say that you're in hyperbolic three space, and I'm going to take the upper half space model. And so I have my point at infinity. Then basically the group of translations, the group of isometries that preserves at infinity is isomorphic to, so it's H3, fixing also the point at infinity is isomorphic to R2, which is just translations.
Mm-hmm.
And when I look at my automorphism group, what will happen is I'm going to have a horosphere, so which I'm drawing here. So a horosphere is this R2 with this one point at infinity. And now my automorphism group that preserves the point at infinity is isomorphic to a Z2 inside R2. And so when I look at my automorphism, there are different ways in which I can converge to infinity. I could, for example, take one generator and just apply it many, many, many times. So diverge off to infinity in this way. If I take another generator, I'll also diverge to infinity, but kind of from a different direction. And so we see, let me say that this is generated by T1 and T2. So remember I said that I had, for any T, I had this limit that if I take my automorphism and I push a Kähler metric normalized by n squared, this converges to some limit, I denoted Q pi of T. So as n goes to infinity, this converges to some limit. But if I take T1 and I take T2, in general, these limits will be different. So, so this is why I kind of have associated to this one point at infinity, I have kind of a whole, in some sense, sphere of positive currents, because the reason I'm saying a sphere is because if I rescale T by a multiple, I just rescale this current. So really I have to kind of choose a direction on this, in this R2 in which to go off to infinity. And the way it manifests itself in the proof of the theorem is the following. You see, if I take an irrational geodesic, so this is now in hyperbolic 3 space. This is my horosphere. Then when I try to follow it, right, so it's going towards this point at infinity, and when it enters the horosphere, it has many options where to come out. So it could come out essentially, you know, here or somewhere here. My drawing skills are not very good, but you have, if it doesn't go off to the point at infinity, it will come out, but it will have traveled somewhere, you know, very far in this direction. So I mean, of course, it will look like this, but I kind of want to track it in the horosphere. So I kind of cut it off. I project, I kind of cut and project, and then I follow it later. So for this reason, as soon as my ambient hyperbolic space is more than 3-dimensional, so it's 3 dimensions or higher, the hyperbolic space, then I have more options to kind of enter and exit the horosphere, and they all contribute different currents in the limit.
And so this blown up cone should be considered as a kind of more precise model of this compactification, right? Which of the Kähler cone.
Yes, so it's kind of it's a more refined compactification, yes, because you have to blow up the rational points.
Mm-hmm. Yeah, that's beautiful. So some more questions, please. Okay, so then let's thank Simion again.